Okay, welcome to the evening section of today's meeting. Be careful on the subtitles. We have two talks on the NCAR CSM and one talk on not yet finished physical parameterization by me, and another talk on the dynamical core development in Central Weather Bureau. So first, let's welcome the first speaker, Hua-Lu Pan.
Let me first thank the organizer for giving me so much time to talk. I really don't need an hour and 20 minutes. So I will yield some of my time to the other speakers. I'm going to talk a little bit about what we envision as the CCliCS coupled GCM. This started a few years ago when Huang Xiong told me that Taiwan has many groups doing each own climate model studies and climate impact studies, but there is a desire to have a unified effort so that everybody's effort could be coordinated. And in order to do that, we talked about that you've got to start with a coupled global circulation model. Without that, your regional downscaling, your scenarios, time slicing, all of that would not work well. So we talked about how do we go about doing this. Given that to really build a brand new model would require more resource than Taiwan could really put together, we thought we would be more practical. So this is what we came up. We thought we want to have a model that we could run locally. The computing resources are becoming cheap enough that we could run a global model locally nowadays, and so that we could perform scenario simulations and we can archive high-resolution data. This would be a starting point for all the downstream researchers who need data, who need to perform sensitivity studies and so on, would have one. And if we could afford it, it would be nice to have a model that could provide independent estimates of global change impact. And that would make the effort of building a global model worthwhile. So since we considered all the resources that we have, we decided, given these resources, we need to be more focused than a plan to develop a complete model. I think China is ambitious, wanting to develop a complete set. We shouldn't be so ambitious. So we thought about it. The idea is then we would try to adopt the NCAR CSM as the base model for several reasons. One is they're well documented, they're well supported, and they have a reasonable dynamic core. It's not written by SJ, but it is following SJ's principle. And so we think that really to do the climate impact, probably making an effort in the physics change would be a more economical way to do this problem. So we intended to modify the parameterized physics to do this problem. And what we want to do is really try to build a core of personnel, and this is where RCEC is the place that can put this together, to have several people that Huang Xiong has tried to recruit over the last 2 years, and to have people who can sustain the development not just running something that comes from the outside world. And I think that is the long-term goal, is to have our own unique set of models which can provide useful information to the world, at the same time be a tool for the local development, local climate researchers or users, okay? So we decided to focus on two aspects in terms of the physics, both of them having to do with moisture. In terms of convection, our first step would be to use and modify the NCEP GFS physics in terms of convection and turbulence. And this is sort of because, as Huang Xiong has said in his introduction, this has been developed for the weather model, so that it is really trying to generate disturbances on the, essentially weather variations, which hopefully with something that the current climate models has been criticized. And the other part is the microphysics. And this is primarily because JP has been working on this for many years. And because we all recognize the cloud aerosol radiation interactions are going to be one of the key elements for the next generation climate model study development. So our plan is to do this, and currently we've already ported the Chem 4 and Chem 5 and run them successfully here, and data is already available. So as a first step, we will be able to provide data to start coordinate users in the various universities. And we've ported the GFS package, but we're still under testing. This is primarily because we've got 4 or 5 new people who are joining the modeling world, and they have to learn to develop. And I think that learning and development is as important a part of this project as actually having the model to run. And I think we're very close to having this package considered successfully implemented, and we should be able to assess the impact. And we are starting to discuss the connection of the microphysics to the GCM. And this is where I have stayed away from the microphysics aspects of the model for many, many years. I've just concentrated mostly on this part, on the convection side. And I realized that at NCEP in the last 10 to 15 years, we have been trying to implement a more sophisticated microphysics scheme than what we currently have, which is the basic bulk Sunquist type scheme. And we have not been successful. NCEP has a very high criteria to decide when a scheme can be implemented, and you have to improve the skill scores of your forecast. You cannot just say, oh, this is a better scheme, we'll put it in. And so when you cannot not just improve, when you can't even compete with the current operational scheme, there's no hope of getting that into operation. So about 2 years ago when I retired, I decided I'm going to take a look at this aspect of the problem. And I think this is what I see as the issue, okay? That the modern day microphysics, they're really built for very high resolution models. So they are intended to function when the grid point is saturated to supersaturated. But for the kind of GCM resolution that we envision to run here, even if we go to 25 kilometers, this is still a very stringent requirement. You have to wait for the whole grid point to saturate to have cloud. You're not going to get the right amount of cloud. So there's a practical issue. So then we start to say we have to face the issue of fractional clouds. And there are various people who looked at this fractional cloud for some time, and the treatment are still fairly arbitrary in my mind. So I decided we're going to try to look at it from a unified point of view. And I started because a lot of people have been looking at the probability density function-based method to specify cloud amount. And as I looked into it, I realized that to deal with fractional cloud, it's not just the cloud amount that's the issue. The issue is also the condensation and evaporation in an unsaturated grid. And this is, NCAR has put those together, called it a macrophysics. And they create the input to the microphysics, okay? And in addition, fractional cloud area require treatment of cloud and cloud-free portion of the grid in microphysics. So we have to learn to deal with both of these if we want to couple JP scheme into the global model, okay? So I'm going to try to start with a very simple, basic PDF. I'm going to assume that the distribution is uniform, and I want to go through the whole scheme to understand where we need to use where there are arbitrary assumptions that we can get rid of, and where are there things that we can do it consistently. And I'm saying that the real issue is the computation of condensation or supersaturation. And in principle, we don't have to generate condensation. We could just make supersaturation and let the microphysics deal with the condensation process itself, because for ice cloud and so on, they are different. So now this is a simple PDF. If you take the Q variables and the probability function here, I'm just going to assume it's a block. And then you can compute the cloud fraction, and you can compute this delta, which is the distribution width. This is the two key quantities that we use in the PDF scheme. Okay. So I'm repeating again. So for high resolution models, you can just wait for the grid to become supersaturated. In low resolution model, I think Chem5 is starting to do it differently, but mostly you have to go from 0 to something. In other words, if a grid doesn't have cloud and you start to moisten up, you have to know when cloud is going to form. So a lot of people use the RHC concept to do this. Okay, this is so-called critical relative humidity. The RHC seems a reasonable thing to do. You need something to start condensation. And there has been people who have linked the RHC to be the starting point of condensation under the uniform distribution assumption. But the problem I see is that Sundquist used RHC to calculate anything else, and that's what I have trouble with. Okay, so I'm just going to show that you can derive RHC from the uniform distribution. I'll jump in fairly quickly now. The key thing is this environmental humidity, because your QV is the average for the whole grid, QL. And for the cloud-free region, we need to know what its humidities are. And you can show that the environmental portion can be reduced to something that's related to the cloud fraction and the distribution width. And from here, we will now look at a special case when there is the maximum of the distribution is at saturation, so that cloud, anything more moist than this, cloud should form, because you're going to go into, there will be Q that's greater than Q sub S. And Sundquist famously wrote this equation without proof or discussion, and he says, this is the relationship we're going to use. And I'm just going to show quickly that if you use this equation and you use the special case when this happens, so that delta is critical delta and RH is critical RH, you can derive indeed this equation, which is exactly what Sundquist had. So I think Sundquist in his mind had the uniform distribution, but this is at a time when, you know, modelers, ancient modelers like me, you don't add another prognostic variables. You think, well, if I don't have to do it, I don't. So if you cannot carry delta and you cannot carry our cloud fraction, then you have to come up with some way to do this. So essentially, if you review, if you see what that is doing, and you can reformulate the whole problem is if you have a moisture convergence, how much of it goes into the cloudy portion to either become condensation or supersaturation, how much of it goes into just moistening the environment. Same thing with evaporation. If you have large-scale drying, how much of it goes to one way or the other? And if you do it by making the proper distribution assumption, then you're okay. And so that's what we're going to try to use to link JP scheme to the CESM. Okay? So since I still have another hour, I will just finish it up quickly. So our proposal will be use RHC only in the initial formation of cloud. When there's no cloud, you have to have something, and that has to be a grid size dependent. Once cloud exists, then we will only use PDF to describe the cloud, and there will be no use of RHC, and the entire thing would be self-consistent from radiation to the macrophysics. And so, and I'm just using the simplest PDF. We can certainly apply higher order schemes in the future. Thank you very much.
Thank you, speaker. We'll take a few questions. We have 5 minutes.
Well, it's interesting, I think. But I'm just curious if you know the PDF of updraft or downdraft or whatever, does that help more? Because you know the CSM actually the so-called cloud formation for stratform actually is now based on more physical-based boom model, which is you know the coupled with aerosol together. So that's generally you need to know the PDF of updraft or the turbulence kinetic energy. So in order to do that, so that's a very sophisticated boom model, but parameterized.
You could, in principle, if you know the cloudy portion is the updraft region, yeah, you can use that instead of. But it's so. I'm choosing the simplest PDF to illustrate the whole procedure of, you know, consistent calculation. Once you've done that, you can choose the PDF that is more appropriate for different situations. And certainly, there's not a need to have a single PDF with all the functions. Certainly.
Any other questions? We have plenty of time. Okay, let's thank the speaker again.